In this lesson, we will learn how to find area and arc length of curves where they are represented by polar coordinates. So how do you find the area of a polar region bounded by the polar curve r equals f of theta and by the rays theta equals a and theta equals b, where the difference between b and a is less than 2 pi? So what we have to start with is how to find the area of a sector. So let's think about the area of a semicircle. So the area of a semicircle is 1/2 pi, we'll say r squared. Now if I only had a certain portion of that circle, say an angle theta, the area of that sector is 1/2 r squared theta. Which you can think about the semicircle, that's for a specific case where theta equals pi. So we have the area of a sector of a circle with, my picture doesn't make any sense. So if we have the sector of a circle with length side r, angle theta, that's how you find the area of that sector. So suppose now you have some polar curve bounded by theta equals a and theta equals b, and there's some weirdness, like that in the middle. So you start like we almost always do by dividing this region into smaller regions. And the curve that describes these radii is r equals f of theta. So the area of the ith slice is about equal to 1/2. Pick some theta sub I star in the interval. That represents your radius, multiplied by delta theta. So whatever the change in theta is. And then the total area is found by adding those up, so approximately equal to the sum from I equals 1 to n, 1/2 f of theta sub I star squared delta theta. And the area is found exactly using a limit as n goes to infinity, which then becomes the integral a to b 1/2 f of theta squared d theta, which you could also write as 1/2 the integral from a to b r squared d theta, either way. So let's find the area enclosed by one loop of the rose curve r equals 3 cosine of 2 theta. So what we're going to have to do first is graph this rose loop, and since I know this is hard, let's go over it in detail. So cosine of 2 theta will have period pi, making that pi over 2 and that pi quarters. Starts off at 3. By pi quarters we're down at 0. By pi halves we're down at -3. Then back up at 0, and then back up at pi. So that's in rectangular coordinates. Now transferring that into polar coordinates, we start off at angle 0 radius of 3. By pi quarters we're back down to 0. And then by, this is pi over 2, we're at -1, which puts us down there, also a distance of 3. And then back up to 0. By pi, we're back at a radius of 3. And then continuing the pattern, next we'll have 2 pi, 3 pi over 2. So by 5 pi quarters, we're back at 0. By 3 pi over 2, we're down at -3. So we go 3 pi over 2, reflect up, and then by 7 pi quarters, we're back at 0. This would be over in this quadrant, but it reflects over, and then back to 2 pi. So there will be many integrals that will find the area just enclosed by one loop. Let's just look at this particular loop here. That can be found, so that came from 7 pi to 2 pi. 7 pi could be the same thing as negative pi quarters. So we can find the area using this 1/2, the integral from a to b, f of theta squared d theta, with a equaling negative pi quarters and b equaling pi quarters. So that will be 1/2 times the integral from negative pi quarters to pi quarters, squaring the cosine of 3 cosine 2 theta will give us 9 cosine squared 2 theta d theta. So this is the same thing as 9 over 2 times twice the integral from 0 to pi quarters, cosine squared 2 theta d theta. So that's the same thing as 9 times the integral from 0 to pi quarters. Now you have to remember how to integrate cosine squared of 2 theta. Now to integrate the cosine squared of 2 theta, we're going to use the identity cosine squared theta equals 1/2 1 plus cosine of 2 theta. And instead of theta, we have 2 theta, so we'll have 1/2 1 plus cosine of 4 theta d theta. So that gives us 9 over 2 times theta. The antiderivative of cosine is sine, so we'll have 1/4 sine of 4 theta from 0 to pi fourths. So now let's input our values. So inputting pi quarters, we'll have 9 over 2 times pi quarters plus 1/4 sine of pi minus, I said pi, I wrote theta, whoopsies, sine of pi minus 9 over 2 times 0 plus 0. So that last term is just 0. So in the end, sine of pi is 0, so we just have 9 pi over 8. Find the area of the region lying between the inner and the outer loops of r equals 1 minus 2 sine theta. So we actually graphed this in a previous lesson, but let's do it again. So first let's sketch the curve in rectangular coordinates. We'll have the theta axis, the r axis. Now 1 minus 2 sine theta, so that will be this sine curve, which was like this. So having a highest and lowest point of, actually not like that, it will be reflected first because of the negative, and then shifted up 1. So this point that's 0, that will now be 1. This point that was negative 2, so that's at pi over 2, that's now negative 1. By pi, I'm back up at 1. By 3 pi over 2, my curve is all the way up at 3. And by 2 pi, my curve is back down at 1. And recall that these intersection points right there, they correspond to when we have 0 equals 1 minus 2 sine of theta, which implies sine of theta is equal to 1/2, and that happens when theta is equal to pi 6 and 5 pi 6. And now if we sketch this curve, it's actually called a cardoid. So we start off angle 0, radius 1. By pi 6, we're down at 0. And the radius is negative 1 when theta is equal to pi over 2. So to graph that, we would have gone up 1, reflected, so back down there. And by 5 pi 6, we're back up at 0. So the kicker there is the inner loop is from theta equals pi 6 to theta equals 5 pi 6. Those are the theta values that construct that inner loop. And then from that point on, when we get to pi, we're back at 1. By 3 pi over 2, my radius is 3. And then by 2 pi, we're back to a radius of 1. So that's the general picture of this curve. Now the outer loop, we can think about it beginning at theta equals 5 pi 6. And what we have to do is go all the way to 2 pi, and that little extra bit down will be an additional pi 6 past. So the ending point is 2 pi plus pi 6, which is 13 pi over 6. And what we're looking for here is the area between these two, so this area. So if we first find the area of the outer loop and then take away the inner loop, that will give us the area of the region between the outer and inner loops. And I'm just going to set up the integrals and leave the nasty gory details of working them out to you. So first let's start with that. So our goal in the end is to do outer minus inner. So the outer loop can be found using 1/2 the integral 5 pi 6 to 13 pi over 6, and then r squared d theta. So r is 1 minus 2 sine of theta, the quantity squared, d theta. So that's equal to 1/2 times the integral from 5 pi over 6, 13 pi over 6. If you do integrate this, first expand it into 1 minus 4 sine theta plus 4 sine squared theta d theta. And you'll have to use that trig identity to simplify that sine squared of theta. And when you work out all the gory details, you end up getting that the area of the outer loop is 2 pi plus 3 root 3 over 2. Now the inner loop is awfully similar, just that instead now the integral goes from pi 6 to 5 pi 6. But it's still the same expression inside the integrand. So if you anti-differentiated that expression once, you can just use it again, using the same sort of, just don't do the work twice if you're integrating the same function. And when you work this out, you end up with pi minus 3 root 3 over 2. And then when you do the outer minus the inner, 2 pi minus pi will give us pi. 3 root 3 over 2 minus a negative 3 root 3 over 2 will end up adding, giving you just 3 root 3. So find the area of the region that lies inside the circle. R equals 3 sine theta, and outside the cartoid r equals 1 plus sine theta. So first let's start by sketching these curves. So 3 sine of theta. So sine of theta looks like this, approximately, just pretend. There's my theta axis, there's my r axis. Now when I graph that in polar coordinates, I start off at 0. By pi over 2, I'm already at a radius of, well, 3. So in between there, I'm like this. And by pi, I'm back at 0. So that's actually going to be a circle. We proved something like that in a previous lesson. And then the cartoid, 1 plus sine theta. So we take our sine curve, which usually looks like this, and shift it up 1. So that point's now at 1, this point's now at 2, that point that was 0 is now at 1, this is there, and that's there. Now let's use this blue curve to graph the cartoid. So at an angle of 0, my radius is 1, so 0, 1. By pi over 2, the radius is up at 2. By pi, the radius is back at 1. And between pi and 3 pi over 2, the radii decrease until they're nothing. And then on to 2 pi, they increase back to 1. So it looks something like this. That little bitty part, the radii decrease, increase. So now, if we're looking for the area of the region between these curves, we have to figure out where 3 sine of theta is equal to 1 plus sine of theta, which tells me that 2 sine theta equals 1, which means sine of theta is a half, and that happens for theta equals pi 6 and 5 pi 6. And so the area is equal to first the area of the outer curve between the rays of pi 6 and 5 pi 6. So 1/2 pi 6 to 5 pi over 6, 3 sine of theta quantity squared d theta, minus 1/2 times the integral from pi 6 to 5 pi 6, 1 plus sine of theta squared d theta. Now, taking advantage of some symmetry here, we can instead do twice the integral from pi 6 to pi over 2. And that would be 9 sine squared theta d theta minus 1/2 pi 6 to pi over 2. Expanding that all out, we have 1 plus 2 sine theta plus sine squared theta d theta. Now that 2 will cancel the 1/2, and we can combine those integrals into 1, giving us one big old integral from pi 6 to pi halves. Now that 9 sine squared theta minus a sine squared theta will give us 8 sine squared of theta. And then minus 1 minus 2 sine of theta d theta. And once again, we have to convert this sine squared theta into regular sine theta using the double half-angle identities. So that will be 8 times 1/2, 1 minus cosine 2 theta, minus 1 minus 2 sine theta d theta. And let's antidifferentiate everything. Well, let's simplify a little bit first. Pi 6 to pi over 2. Okay, that 8 times 1/2 will give us 4. 4 minus that one will be 3. Minus 4 cosine of 2 theta minus 2 sine of theta. And by now you're thoroughly sick of trig functions. So, 3 theta. The antiderivative of cosine will be sine, so sine of 2 theta, 2 of them because it's 4 times 1/2, and then 2 cosine of theta, that should be positive so that the derivatives match up, and then all that evaluated from pi 6 to pi over 2. When we plug in pi 6 into 3 theta, we get 3 pi over 2. When we plug pi over 2 into the sine of 2 theta, we get sine of pi, which is 0, so minus 0. Cosine of pi over 2 is 0 as well. So then minus 3 pi over 6, or pi over 2, minus 2 sine of pi over 3 plus 2 cosine pi over 6. And we're almost done. Okay, sine of pi over 3, just think for a second, that's root 3 over 2. Cosine of pi over 6 is also root 3 over 2, so lo and behold, those two terms cancel. We just have 3 pi over 2 minus pi over 2, which is 2 pi over 2, or pi. Speaking of which, you should go buy yourself some because that problem was so terrible. Now, one problem with finding points of intersections of polar graphs is you can miss points when you set two equations equal to each other. And part of that comes from the fact that you can represent these curves in more than one way. So the points that you missed might be found by using a different representation of the curve. And so what you should really do instead is graph the curves and then check and see if they do indeed intersect at those points. So let's do an example. Let's find all points of intersection of the curves 1 minus 2 cosine of theta and r equals 1. So it's good practice for graphing these polar curves. So 1 minus 2 cosine theta. So let's first sketch this in rectangular coordinates. So first of all, negative 2 cosine theta equal to r. So I'll have a period of 2 pi. It will start at negative 2, be 0 by pi halves, be positive 2 by pi, back down to 0, back down to negative 2. So there is the graph of negative 2 cosine of theta. Now if I graph 1 minus 2 cosine theta equals r, it takes that blue graph and shifts it up 1. So this point is now at negative 1. This point that was at 0 is now at 1. This point that was at 2 is now at 3. That point that was 0 is 1. This point that was negative 2 is negative 1. And let's figure out where these zeros are, because those are possibly going to be important. So 1 minus 2 cosine of theta equals 0, when 1 equals 2 cosine of theta. Or when cosine of theta is a half. And now cosine is 1/2 at, I guess that's pi over 3. So I was thinking about my unit circle. 1/2 at pi over 3, and I guess that's 5 pi over 3. Okay, so now let's sketch that curve. So when I start off at an angle of 0, I have a radius of negative 1, so I'd go reflect that point back there at negative 1. By pi thirds, I'm at 0, so that will be angles over here reflecting down this way, which means my curve is traversed that direction. And from there, by pi over 2, I'm up at 1. By pi, we're up at 3. By 3 pi over 2, we're back at 1. And then by that 5 pi over 3, we'll be back at 0, and we'll finish off that sideways cardioid. Okay, and recall that this distance was 1 and this distance was 1. Now the curve r equals 1, it's an easy one, a circle of radius 1. So there we go. And you can see from the picture that there are 3 points of intersection. Let's see how many we find when we set the curves equal to one another. So if I set 1 equal to 1 minus 2 cosine of theta, that tells me that 0 equals negative 2 cosine of theta, which occurs when theta is equal to pi over 2 and 3 pi over 2. So I have the points 1 comma pi over 2 and 1 comma 3 pi over 2. So there we go. That's this point and this point. Now the other point came from, that's an angle of radius of 1, actually radius of negative 1, angle of 0. And that one isn't found by setting the curves equal to one another, so you have to use the picture to find that one point. Just recall that came from this dot right here, which meant that you had an r of 0 but a radius of negative 1, so r theta. Let's find all the points of intersection of cosine of 2 theta and 1/2. So we actually sketched cosine of 2 theta in a previous lesson. This time I'm not going to do it again. So it ended up being this rosy curve. Oops, except for it doesn't intersect itself, like this, roughly speaking. And then that shouldn't really say theta equals 1/2. That should really say r equals 1/2. So a circle of radius 1/2. And I think it's pretty obvious that that's going to intersect this curve 1, 2, 3, 4, 5, 6, 7, 8 times. So let's see what happens when we set the curves equal to one another. So if I set 1/2 equal to cosine of 2 theta, so I know that cosine of theta is 1/2. So thinking about my unit circle, the cosine is 1/2 if theta is equal to pi 6. Oops. No, cosine is 1/2 at pi thirds. At pi thirds and at 5 pi thirds. And to get that entire picture of that cosine 2 theta, we had to go around twice. So the next point would be 7 pi thirds and 11 pi thirds. And so 1/2 will equal cosine of 2 theta if 2 theta is equal to any of these numbers. So pi thirds, 5 pi thirds, 7 pi thirds, 11 pi thirds. And then dividing each of these by 2, we get theta is equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So there are 4 of the thetas, which looks like we have this point, that point, and that point. So effectively every other one. But it looks like also theta equals pi thirds is an intersection point, as is theta equals 2 pi thirds, and then 4 pi thirds, and 5 pi thirds. If you want to, those can be solved by we're noticing that this r equals 1/2 could have also been r equaled negative 1/2. That's the same circle. a negative radius doesn't make much sense, but there's this reflecting business going on, so it produces the same graph, and setting negative 1/2 equal to cosine of 2 theta. When you solve that equation, you get the blue points of intersection. Next, let's find the arc length of a polar curve r equals f of theta. So recall that the length of a curve in the parametrized form was given by an integral from a to b. Instead of t, you will use theta, dx d theta squared plus dy d theta squared d theta. And then if you recall that x is equal to r cosine theta and y is equal to r sine of theta, we can derive a formula specifically for this parameterization. So integral from a to b. Now dx d theta will be dr d theta cosine theta minus r sine theta, that quantity squared, plus dy d theta will be dr d theta times sine of theta plus r cosine of theta, that whole thing, squared d theta. And if you expand this all out, it gets really, really ugly. A to b root. Okay. So what we'll have will be dr d theta squared cosine squared theta minus 2 dr d theta cosine theta sine theta, and there's also an r there, I guess, that plus r squared sine squared of theta. It's just the first one. The next one, plus dr d theta squared sine squared theta plus 2 dr d theta r sine theta cosine theta plus r squared cosine squared theta. And before you decide to quit this class right now, notice a couple things. This and that cancel, thank goodness. And cosine squared plus sine squared is 1, so with this term and this term you could factor out the dr d theta squared, and you'd have dr d theta squared times sine squared plus cosine squared. So the integral from a to b root dr d theta squared cosine squared theta plus sine squared theta, and then plus r squared times sine squared plus cosine squared theta d theta. And now this will equal the integral from a to b, the root dr d theta squared plus r squared d theta. So that's the formula we're going to use, not the super long disgusting one. We are going to use one that's already been simplified. And in many cases, all I will ask you to do is set up the integral, not solve it, because they can get very tedious very quickly. I tried to solve one that another textbook just said, oh, you do the substitution, it's really, really easy, and it comes out to be 8. And the substitution turned out to be not so easy, it was awful, it would have taken a whole page, and I just gave up. So let's set up, not. So set up a curve, an integral, to find the length of the cartoid r equals 1 plus sine theta. So the length will be equal to, and I'll go from a to b, root dr d theta squared plus r squared d theta. So this cartoid, which we actually graphed in an earlier example, is traced as theta ranges from 0 to 2 pi. Now dr d theta is cosine of theta, so cosine of theta squared plus 1 plus sine of theta, the quantity squared, d theta. And let's just simplify this a little bit, even though we're not going to work it out all the way. So cosine squared theta plus 1 plus 2 sine theta plus sine squared of theta. And cosine squared plus sine squared is 1, so this gives us the integral from 0 to 2 pi, the root of 2 plus 2 sine of theta d theta. And if you're brilliant, this integral actually works out to be 8, but I think getting it set up and simplified is totally good enough for me. Find the length of the arc from theta equals 0 to 2 pi for this other cartoid. F of theta equals 2 minus 2 cosine theta. So once again, the length is traced as we range from 0 to 2 pi, root. So first we have dr d theta squared plus r squared d theta. So let's just plug those things in. So dr d theta, the derivative of negative cosine, will be positive sine, so we'll have 2 sine of theta, the quantity squared, plus 2 minus 2 cosine of theta, that quantity squared. So 4 sine squared theta plus 4 minus 4 cosine of theta plus 4 cosine squared theta d theta. And that will be 2 pi. So combining this term and this term, we'll have 4 times sine squared theta plus cosine squared theta plus 4 minus 4 cosine of theta. So that will be the integral from 0 to 2 pi, the root of 8 minus 4 cosine theta. And one more thing you could do technically would be to factor out a 4 and square root it, and make it 2 times the integral from 0 to 2 pi, root 2 minus cosine theta d theta. It seems so simple, but it's not very easy to integrate that. So let's just set it up and not solve it. The final thing we will consider is the area of a surface of revolution. So we have some curve. Let's suppose first of all we have rotation about the polar axis. So the way I would think about surface area is this, is you have a little slice, and the first thing you have to do is find the circumference of that slice, so 2 pi r, and then the length of that slice. So the surface area could be given by 2 pi integral from alpha to beta. In this case, with rotation about the polar axis, the r is given by the y-coordinate, and the y-coordinate is r sine of theta. And we have that r would equal this f of theta curve. Anyhow, it's r sine of theta, and then times the length of the curve, which is the thing we just discussed, r squared plus dr d theta squared d theta. So that would be if we rotate about the polar axis. Now if we rotate about the line theta equals pi over 2, that corresponds to this, and all that will change is it'll be 2 pi x, and x is given by r cosine theta, so alpha to beta x, well, not x, r cosine theta, and still the same expression for the length, the root of r squared plus dr d theta squared d theta. So let's find the area of the surface formed by rotating the circle f of theta equals cosine theta about the line pi equals 2. So first we have to graph cosine of theta and figure out what values of theta constitute like the beginning and end of that curve. Alright, so if we just graph a cosine, regular old cosine. Okay, so there's pi over 2, 3 pi over 2. Now graphing this in polar coordinates, we start out at 1. By pi over 2, we're back at 0. And then down here, that's at pi, we're at negative 1. So that would reflect over to this point, and then we'll repeat everything. So